Hey everyone, and welcome to another deep dive with us. Today we'll be exploring the world of data mining.
Sounds exciting.
It is. Our roadmap for this deep dive is the book, Introduction to Data Mining.
A classic.
It is. And whether you're working on a data science project or just curious about data mining, this deep dive is for you.
Absolutely. Data mining can be applied to so many different fields, from business to healthcare to even scientific discovery.
Right. And to help us navigate this fascinating world, I'm joined by an expert who can make even the most complex algorithms seem understandable.
I'll do my best. I'm excited to dive into this book with you.
Let's get started then. Chapter 1 focuses on avoiding false discoveries.
A crucial topic. It's so easy to get caught up in finding patterns, even when they don't actually mean anything.
Exactly. It's like thinking you found a pot of gold, but it turns out to be fool's gold.
Exactly. And in today's data-driven world, it's more important than ever to be aware of this.
Couldn't agree more. The book uses high-speed stock trading as an example. Algorithms making split-second decisions based on data.
Talk about pressure. But high-frequency trading is just one example. Data mining is used in so many different industries.
It really is. Personal recommendations,
Yeah.
fraud detection, you name it.
Right. And one of the biggest challenges in data mining is scalability.
With the amount of data growing exponentially, that makes sense.
It does, and that's where efficient algorithms and data structures come into play.
Definitely. Speaking of history, I found the origin story of data mining really interesting.
Oh, yeah. Tell me more.
It emerged from workshops in the late 1980s. Researchers from different fields came together to try to extract knowledge from databases.
It's fascinating how it mirrors the data science boom we see today.
It really does. So it seems like collaboration has always been key in this field.
Absolutely. It's a truly multidisciplinary field, which is what makes it so exciting.
I agree. Okay, let's move on to Chapter 2.
Yeah.
Data itself. The book breaks down different attribute types.
Nominal, ordinal, interval, and ratio,
Right. And they use temperature scales as an example.
which I thought was a great way to illustrate it.
Yeah, me too. It shows how the same data can be interpreted differently based on the scale.
Exactly. Understanding the nature of our variables is so important.
It really is. And then they get into different data set types, which is where things get really interesting.
Like representing chemical compounds as transactions.
Yes. It's like applying market basket analysis to the molecular world.
Exactly. And it highlights how the way we represent data shapes the possibilities for analysis.
It's like opening up a whole new world of possibilities. Now let's talk about data quality, which is something no data miner can escape.
True. Cleaning data, handling missing values, it's all part of the process.
And the book really stresses how crucial this is. They even suggest ignoring missing values when calculating similarities for clustering.
Which can be a valid strategy in certain situations.
Right. But garbage in, garbage out, as they say.
Exactly. We can't expect reliable results if we feed our algorithms bad data.
And speaking of challenges, they introduce the curse of dimensionality.
High dimensionality can be a real headache in data mining,
It can. As the number of features increases, the data becomes sparser.
making it harder to find meaningful patterns.
It's like trying to find a needle in an ever-growing haystack,
The book suggests dimensionality reduction techniques to tackle this.
like PCA. It helps simplify the data by reducing the number of dimensions,
while preserving as much information as possible.
like creating a map of the data, highlighting the most important areas.
A great analogy.
And to wrap up Chapter 2, they discuss feature selection, choosing the most relevant attributes.
Picking the right ingredients for our data mining recipe.
Exactly. Making sure we have the right mix for a delicious and insightful dish.
And there are various methods for this, like filter methods, wrapper methods, and embedded methods.
Each with its own advantages and disadvantages.
Right, it's about being strategic and selective in our analysis.
Absolutely. Now, are you ready to move on to Chapter 3 and get into classification?
Let's do it.
This is where we start building models to predict things like loan approvals or customer churn.
And the book dives into decision trees, which are a great place to start.
I love decision trees. They're so easy to visualize, like a flowchart guiding you through the decision process.
They are. The book starts with Hunt's algorithm, a classic for building these trees.
And then they get into splitting criteria, choosing the best points to split the data.
Like the Geni index and entropy. They might sound intimidating.
They did to me at first. But the loan default prediction example really helped me understand.
It's all about finding the splits that create the purest subsets, where data points belong to the same class.
Like sorting laundry, separating whites from colors to create neat piles.
I like that analogy.
Thanks. And then they explain how to handle continuous attributes, which can't be split for every single value.
They suggest sorting values and finding the midpoint to create meaningful intervals.
Makes sense. And then, of course, we can't forget about overfitting.
The nemesis of every data miner.
It really is. It's like memorizing answers instead of understanding the concepts.
The book suggests techniques like pruning and model selection to combat this.
Pruning simplifies the tree, while model selection helps choose the best model from a set of candidates.
Using techniques like cross-validation to evaluate their performance.
So it's about finding the right balance between complexity and simplicity.
Exactly. Making sure our model captures the essence of the data without getting bogged down in the noise.
And speaking of finding patterns, let's move on to Chapter 4, Association Analysis. This is all about those fascinating relationships between items in data sets.
Like people who bought this also bought that patterns, the classic market basket analysis.
Exactly. And the book starts by introducing frequent item sets.
Those sets of items that appear together frequently enough to be interesting.
Right. And we need to define a minimum support threshold to determine what's frequent enough.
Like saying an item set needs to appear in at least 5% of transactions to be considered frequent.
So once we have those frequent item sets, how do we go from there to actual rules?
That's where association rule mining algorithms come in. The book introduces the a priori algorithm.
The a priori algorithm.
It's a clever way to find those patterns efficiently by crooning the search space.
Like eliminating impossible paths in a maze, focusing on those that might lead to treasure.
Exactly. And then they introduce the FP growth algorithm, which is even faster.
It uses a special data structure called an FP tree.
Right. It's a compact and efficient way to represent the data.
So it's all about speed and efficiency. Now, we have our rules, but how do we know which are truly interesting?
That's where objective measures of interestingness come in.
The book focuses on support, confidence, lift, and correlation.
Each giving us a different perspective on the relationship between items.
And they highlight a challenge: cross-support patterns, those misleading associations driven by high-frequency items.
Like thinking milk and bread are strongly associated just because they're both popular.
So we need to look beyond simple metrics and consider things like lift and correlation.
Exactly. We need to make sure we're not fooled by superficial correlations.
Okay, let's move on to Chapter 5, Cluster Analysis. This is all about grouping similar objects together.
Like sorting socks or organizing books.
Exactly. It's about finding natural groupings in data to reveal patterns.
And the book explains the two main categories: partitioning methods and hierarchical methods.
Partitioning methods, like k-means, aim to divide the data into a predetermined number of clusters.
It's like a game of musical chairs, where each data point wants to find its closest center.
A fun way to think about it.
And then we have hierarchical clustering, which builds a hierarchy of clusters.
Like creating a family tree of clusters.
Right, and they explain different linkage criteria, like single link, complete link, and average link.
Which determine how the distance between clusters is calculated.
Each one leading to different types of hierarchies.
Then they introduce DBS scan, which can handle clusters of arbitrary shapes.
Unlike k-means, which tends to create spherical clusters.
Right, and they explain the concept of core points, border points, and noise points.
Core points are the heart of the cluster. Noise points are the outliers.
And finally, they discuss cluster evaluation. How do we assess the quality of the clusters we create?
We want clusters that are cohesive internally and well separated from each other.
So it's not just about creating clusters, it's about making sure they actually make sense.
Exactly. That's it for this part of our deep dive.
Stay tuned for Part 2, where we explore even more powerful techniques.
It's going to be an exciting ride.
I can't wait.
Welcome back, everyone. Ready for more data mining?
Absolutely. I'm excited to see what other techniques we can add to our toolkit.
Great. Well, in this part, we're moving beyond decision trees and exploring alternative classification techniques.
That sounds intriguing. What's first on the agenda?
Rule-based classifiers. They're actually closely related to association analysis. Remember those people who bought this also bought that patterns? Well, rule-based classifiers use those associations to actually predict class labels.
So instead of just uncovering those relationships, we're using them to make predictions.
Precisely. For example, a rule might say, if a customer buys diapers and beer, then they're likely to buy baby wipes.
Okay, I see. So we could use that rule to predict future purchases and maybe even target recommendations,
Exactly. The book talks about evaluating the quality of a rule set, focusing on two key aspects:
which are
mutually exclusive and exhaustive.
mutually exclusive, exhaustive. Can you elaborate on those?
Sure, mutually exclusive rules mean each instance is covered by only one rule, so there's no ambiguity in classification.
Like if a customer buys diapers and e-beer, they should only fall under one rule, not both.
Precisely. And exhaustive means every possible instance is covered by at least one rule.
Makes sense? So a good rule set needs both of these qualities.
Exactly. They introduce an algorithm called sequential covering for building these classifiers.
Sequential covering, okay.
It basically builds the classifier one rule at a time, starting with the rule that covers the most instances.
So it's a step-by-step process, adding rules to cover the remaining instances.
Right. And they mention a specific algorithm called IEP, which is known for its robustness.
Cool. So from shopping carts to rule-based classifiers, what's next?
Nearest neighbor classifiers. These are pretty intuitive. You classify an instance based on how similar it is to known examples.
So it's like judging a book by its cover.
In a way, yes, except here the cover is the set of nearest neighbors.
Make sense?
It's a lazy learning approach, meaning it doesn't explicitly learn rules, it just stores the training data.
Interesting. And then uses that data to make predictions on the fly based on similarity.
Exactly. They talk about choosing the right value of k, which is the number of neighbors to consider.
Ah, right. And the distance metric also matters, right, to measure similarity.
Absolutely. Both k and the distance metric can impact the classifier's performance.
Gotcha. So what other classification methods are out there?
Probabilistic classifiers. They add a layer of nuance by quantifying uncertainty in predictions.
So instead of just saying this customer will churn, it might say there's an 80% chance this customer will churn.
Exactly. It gives you a probability or confidence score.
That's really helpful for decision making.
It is. They focus on the naive Bayes classifier, which is surprisingly effective.
Naive Bayes. Why is it called naive?
It makes a simplifying assumption that attributes are conditionally independent given the class label.
Which might not always be true in real-world data sets.
Right. But despite this assumption, it often performs quite well.
That's interesting. They also mentioned Bayesian belief networks, which seem more sophisticated.
They are. Bayesian networks allow you to model more complex dependencies between attributes.
They use a graphical representation, right? Like a network of nodes.
Exactly. It helps visualize the flow of information and influence between variables.
And then there are factor graphs, which help break down the probability distribution.
It's like taking apart a complex machine to see how each part works.
I like that analogy. And of course, we can't forget about artificial neural networks.
Ah, yes. ANNs back again. This time, we're going deeper into their workings.
Gradient descent, activation functions, it gets pretty complex.
It does. They talk about backpropagation, which uses gradient descent to adjust the weights and minimize error.
So it's like the network is constantly learning and improving.
Exactly. They also talk about deep learning, with its multiple hidden layers.
Allowing the network to learn those complex hierarchical representations of data.
Right. And the choice of activation functions, like ReLU, is crucial for the network's success.
And the loss function too, like cross-entropy, which is often used for classification.
Exactly. It's all about optimizing each component for the best performance.
And they introduced stochastic gradient descent, which is more efficient for large data sets.
Because it updates weights using small batches of data instead of the entire data set.
Makes sense. Now, what about support vector machines? Didn't we talk about those before?
We did touch upon them, but now we're delving deeper. They're powerful linear classifiers that find the optimal hyperplane to separate classes.
That optimal hyperplane is the one with the largest margin, right?
Precisely, like a line that divides two groups of data points with the widest gap between them.
Okay, I remember that. And the kernel trick extends SVMs to handle non-linearly separable data.
Right. It's a clever technique that allows you to implicitly map data into a higher dimensional space where it becomes linearly separable.
It's like adding another dimension to see patterns that were previously hidden.
Exactly. But choosing the right kernel function is crucial for SVM performance.
It seems like there are a lot of decisions to be made when choosing and fine-tuning these classification techniques.
There are. It's important to understand the strengths and weaknesses of each method and choose the best one for your specific problem and data.
It's like having a toolbox full of different tools, each one suited for a particular task.
Exactly. Now let's move on to Chapter 7, where we revisit association analysis.
Oh, we're going back to association analysis.
Oh. Yes. But this time we're exploring more advanced concepts.
Sounds interesting. Like what?
Well, for instance, they introduce quantitative association rules. These extend association analysis to handle continuous attributes.
Continuous attributes, you mean like age or income, instead of just categorical items?
Exactly. So instead of just people who buy diapers also buy beer, we might discover people who spend over $50 on groceries